All right, let's take a look at this handwritten digit example. And this is what's called the MNIST, or modified NIST handwritten digit example. And as mentioned, it's kind of the hello world of machine learning. And this data set that's publicly available contains 70,000 images of handwritten digits from many, many different people. And it's a great example it's very suitable for image classification. So what we're trying to do is, given this set of images, classify them into one of 10 classes, digits 0 through 9. So typically we'll use 60,000 of these images for training and 10,000 we'll set aside for testing. And each of these digits happens to be an image that's 28 by 28 pixels in size, and along with a label telling us what exactly that value is supposed to be. And this data set has been used over the years for testing different algorithms, and we're going to use a relatively simple deep learning model, but even this model can achieve 98% accuracy, which is close to human level performance. This example uses the Keras library and TensorFlow, which are popular deep learning libraries. You can run this locally because fortunately the model is simple enough and the data set is small enough that you can run it locally. But for more sophisticated models, it's preferred to use it to do this on a GPU instance in the cloud, or if you have a GPU on your own machine. So I'm going to import a bunch of libraries here. I'm not going to go into the specifics, but most importantly, we're going to use this Keras library, which is very easy to use. And these are some parameters: the size of the image, the number of rows and columns, 28 by 28 pixels. This batch size has to do with how we're training it. Not really important for the purposes of this example. The number of classes describes how many outputs we're going to have, and we're going to have one output representing one of 10 digits 0 through 9. And this number epochs, I'm going to change this to 5 for now for our training, because we don't want to spend a lot of time training. If we were to train longer, it would probably increase the accuracy. And what this means is the number of times it's going to cycle through this training data to train the model. All right. And I'm also going to use this value dropout, which has to do with regularization, which improves the quality of the model and reduces overfitting. And we'll talk more about that later. So let me run that cell. So let's load the data. All right, and we've split it into test and train samples. There are 60,000 training samples and 10,000 test samples. We also used a scale factor here. What this does is divides all of the pixel values by 255. If you know anything about graphics, you know that each pixel value typically takes the range between 0 and 255, 0 meaning full black and 255 meaning full saturation, and for a black and white image that would be full white. So we're scaling the values between 0 and 1. All right, let's take a look at a couple of these examples. So if I plot this out, here's one of the images, 28 by 28 in size, and there's also a label. And so the labels are given to us, and this happens to be an 8. Pretty obvious it's an 8. I can look at a few others. All right, that's a 6. And notice they vary quite a bit. Some of them are higher quality, some of them are lower quality, depending on people's handwriting. All right. So down here is a definition of the model. All right, this is a deep learning model. It's a multi-layer model. All right, it has an initial layer which flattens the image. What it does is takes that two-dimensional image, 28 by 28, and turns it into one long vector of values 784 in size. 28 by 28 is 784. And then there are a couple of dense layers and some dropout layers, and also some activations. We'll talk more about that a little bit later, but this has to do with the specifics of developing this model. Fortunately, this model has already been developed, and we can just use it without getting into the details too much. And the output layer has the number of classes, meaning there are 10 outputs, one each representing one of the 10 digits. Right? And then at the end, we're going to print a summary of this model, which will tell us a little bit about how it is been defined. So this summary gives us shows us all the different layers, and there are a number of training parameters that will be trained. These are weights and biases, factors within that model that will be automatically learned. And the total number of parameters that are going to be learned is actually quite large. Almost 700,000 parameters we're going to learn, because you can imagine that the image is quite complex. So it's going to learn all of that. All right. So here we're going to train the model. So let me go ahead and get it started, because it's going to take a minute or so, and we'll watch it progress. So we use this model.fit given the X train data and the Y train data. In the case of X train, that's our images. Those are our sets of images. And the Y train are the labels telling us what it represents. And we are also going to validate against the test data. The X test data would be the test images, and the Y test data would be the expected labels. And once we're done, we'll evaluate it, and we'll print out the accuracy. The accuracy meaning, given the test data, how accurate is the model for all those samples. All right? And we'll also plot out for each epoch, every time it goes through the data, how long, what the accuracy is. And you see, it was going through this training, it was feeding in all of these images, and it was learning, kind of like practicing your golf swing. Keep practicing and try and hit the goal, right? Try and predict the value correctly. And if it's incorrect, it'll make a correction to all its parameters that it's learning. And you can see after 5 epochs, it does get better, right? You notice there's a train accuracy and a test accuracy, and there's a little bit of a difference between the two. And we'll get back to that. That's an important point. It's not super accurate. It's still, in the case of the test, we're up to, let's see, about 97, almost 98% accurate. If we were to run a few more epochs or more time, it would get a little more accurate. There are some limitations ultimately, and we'll talk more about that later. But 97% accurate, that's not too bad. So let's save this model, and we'll save it to a couple of files. We'll save the structure and the learned weights. All right? It's sort of like the knowledge that it has learned. We're saving that. I'm going to go over here to another notebook that I have. And in this one, I'm going to use it for prediction. So I'm going to load my libraries again. And in this case, I'm going to load those weights that I have saved previously. All that training that was done previously, now I can now reuse it. Notice it loads very quickly. And I'm going to reload the data again up for testing purposes only. I'm going to use only the test data in this case. All right. And I'm going to make predictions. I'm going to pass in all the images and push it through the model to make predictions, and it's going to come up with the predictions. And notice that was pretty quick. It turns out that that predictions are much quicker than training. Training takes a lot longer. And what this argmax does is tell me what is the most likely prediction for each value that I put in, the test value. And let's look at a few examples. So I'm going to pick a random image. This random says one of the 10,000 images, and I'm going to plot out the image and also plot out what the model predicted. So the model predicted this is a 1, and the label is a 1, so it got it right. Makes sense. Here's another one. It predicted that was a 4, and that the label is a 4. It's correct. All right, predicted that one is a 7, and the label is a 7, and it looks like a 7, so it's actually doing quite well. It was, 97% accurate, so it's doing a pretty good job of these predictions. So let's take a look at some cases where it's not doing well and try and understand what's going wrong. And this is part of the process of developing a machine learning model, is to understand where it's making mistakes and how we can improve it. So I'll go through 10,000 those samples and find cases where it doesn't match. So here's one. It predicted this one as a 0, but the label was an 8. And if we look at it, it's definitely an 8. And also, if you look at the prediction values, those output layers, right, it gives us a probability of what it believes this was. And it says most likely it's a 0. Most likely it's a 0. But it thinks it possibly could be an 8 as well. So in that case, it made a mistake. And we could have maybe done better if we had a better model, or we had more training data, or we had just trained it with more epochs. So look at this one. Well, what is it? Well, even to us looking at it, we might think it's a 7 or a 2. It turns out the label is actually a 2, but the model predicted 8, so it's predicted something really different. But look at the prediction values. It says it might be a 2 with low probability. It might be a 7 with more probability, but it thinks it's more of an 8. So it didn't do a great job there, but it has some other guesses that might tell us what it might be. So here's one where I can see how it could make a mistake. Right? It says this predicts this as a 1 because it looks kind of like a 1 because even though it really is a 6, and if you looked at this very quickly, human could make that mistake as well. And you see that in the predicted values is that it thinks it might have been a 6 as well. So you see that, and if we try several different ones, we might find ones that, like in this case, yeah, maybe it's a 7, maybe it's a 9. Even a human might make a mistake in that case. Right? All right. So we can go through all the data and look at the error rate, and it says the error rate is 2.19% given all the test data. Now, of course, we could train this longer. We could use a more sophisticated model like a convolutional neural network and achieve even higher accuracy. And some of there are models that are out there that do a very, very good job and actually exceed human level accuracy in some cases. But it gives you an idea how these deep neural networks work and how effective they are given such a simple model. What's interesting, you'll notice in all of these examples, if you look at this model that I showed that's defined here, there are no if statements. There are no conditionals. It's purely a set of mathematical functions that learn from the data. And that's the power of deep learning.